we've learnt essentially the laws that govern gases. But now we're ready to actually do some stoichiometry. But before we do that, we've got to talk about how we practically collect gases in an experiment. Because gases are different than precipitates. Precipitate forms and it settles to the bottom of your aqueous solution and you filter it off and you've got it quite easily, right? So if solids are formed, they're really easy to gather up. We did an experiment where we heated sodium bicarbonate. We didn't have to do anything in the end to find its mass because the solid was sitting there in the test tube. All we had to do was weigh it again. So first we'll talk about vapor pressure and Dalton's law of partial pressure. And let's talk a little bit first about mixtures of gases. In many of our questions, the question doesn't even include what the identity of the gas is. And that's because all gases behave the same way. Whether it's, and I said this the other day, whether it's a helium atom, He, all by itself, or whether it's a carbon dioxide molecule, or whether it's a great big molecule like maybe some evaporating gasoline that contains like 8 carbons and 18 hydrogens. As long as they're in the gas state and they're behaving like an ideal gas, they will exert the same pressure, given the same temperature and volume. They will behave identically. There is no distinguishing between particle A and particle B when it comes to pressure. Everything exerts the same pressure at the same temperature and at the same volume given the same number of moles. And that's what this first statement says right up here. John Dalton hypothesized that gas particles in a mixture behave independently. And I described this to you when we first started talking about gases, right? A gas is a state of matter where there's so much room between the particles that they travel along in a straight line until they run into the wall or they run into another particle. And in order to be an ideal gas, they don't interact. The only way they interact is by a blind collision where they just bounce right off of each other and away they go. And so whether it's bouncing off of a helium molecule or atom, or it's bouncing off of a carbon dioxide molecule, it makes no difference. So gases behave as if they're on their own, as if they're just existing on their own in a big space, no matter how many gases are in that space. So we have a term then called a partial pressure. If each gas then exerts its own little pressure, whether it's alone or not, we can then divide up a mixture of gases into its own little fraction of the pressure. That then eventually results in the overall pressure that we experience. So a partial pressure is that individual pressure that a gas would be exerting on a surface if it were by itself. This image here essentially states that, okay, if I've got some oxygen in a tank here, and I don't know if you can see the little measuring device here, but right there that says 3, right, as if there's 3 pressure units. And if we then had some helium which has 2 pressure units, and we could somehow get all of the oxygen and helium into the same tank, then these particles will bounce around as if they're on their own in their own individual tanks. Oxygen will bounce off of the walls, helium will bounce off of the walls. They won't be aware of the presence of each other. They'll be just doing their thing. But in the end, the pressure in the cylinder will then be 5 pressure units because each gas will be exerting its own individual pressure against the walls, and therefore we can simply add up the partial pressures to get the total pressure. All right? So that's what Dalton's law of partial pressure simply states. Each gas behaves on its own, so if you want the total pressure, we can add up all of the individual pressures of each gas. A good example of that is our atmosphere. You don't need to rewrite the equation there. I didn't even realize it was there, but you can make a statement of that, or you can write the rest of it. But our atmosphere is a classic example of the law of partial pressure. Here I have the top 4 constituents in the atmosphere. And these top 3 are pretty constant. The amount of nitrogen in the atmosphere does not change by much. So this is P with a subscript, and that's supposed to be N2. That represents the pressure of the nitrogen. But I can't have a subscript on a subscript in PowerPoint, so that's why the 2 is big compared to the N. 79.10 kilopascals of the atmosphere is due to nitrogen. Oxygen, 21.22 kilopascals of the air is due to oxygen. Argon is the next most abundant, 0.942. Argon's a noble gas. It's just argon atoms hanging around in the atmosphere. Carbon dioxide then is number 4, and its value, as you probably know, is slowly increasing. People driving cars, cutting down trees. Now there are also many little very small constituents of the atmosphere that are changing depending on the situation. Water vapor is in the air for a short period of time because it rains out. We say it has a short residence time in the atmosphere. So it's very humid out there right now. So therefore, you know, we have high concentration of water vapor. But change the air mass, weather comes through, it rains out, and that changes. Have we totaled up our partial pressures? What do we got? 101.3 kilopascals, which we already know is our standard pressure. So 101.3 kilopascals. Okay? So there's a little application of partial pressure. Now, why have I introduced you to this idea of partial pressure? Well, it has everything to do with the way we collect gases in the laboratory. So let's talk about how we collect gases in the laboratory. First, I need to talk about something called vapor pressure. At any temperature, all liquids evaporate to a certain extent. The vapors produced are in the gaseous state and thus produce a pressure. So all liquids evaporate to some extent, and it exerts a pressure, and we call that vapor pressure because it is vapor coming off of a liquid. Okay? Now this vapor pressure is temperature dependent. The more you heat this, put it in the sun, the pressure would increase. You'd have a greater vapor pressure. More would evaporate. All right? If you heat something so much to the point where it boils, it means that you've increased the vapor pressure so much, you've actually made it greater than the atmospheric pressure, and so it vaporizes so quickly, big bubbles of it come out. That's what boiling is. Boiling is the temperature at which you've made the vapor pressure of the water the same as the atmosphere. We're worried about vapor pressure because we collect gases by pushing water down. It's called the downward displacement of water. So let's talk a little bit about how we collect gases. Now this little picture that I've drawn here is a very crude representation of this device here, which is simply a water trough. All right, so that bottom little bowl, side view of a bowl here, represents, like I said, a very crude representation of a water trough. And there's actually a technical term for that water trough. It's actually called a pneumatic trough, with pneumatic representing gases. So as that gas comes in, so if we've got the gas, then as it bubbles in, as these bubbles rise up, they carry some water with them. So in the end, I have gas plus I have some H2O vapor in there, H2O gas. Because as the bubbles rise through the water, some of it evaporates. And it evaporates because of its vapor pressure. Which means when you're done collecting gas over water, you actually have a mixture of the gas plus the water. So if we were to write this out like Dalton's equation, we would have pressure total is equal to the pressure of the gas plus the pressure of the water. And you'll notice in this equation here, I've simply brought the pressure of the water to the other side to leave the pressure of the gas by itself, which means if I just want the pressure of the gas, I simply have to take the total pressure, the atmosphere, and subtract off the pressure of the water. So I need to do a little subtraction in order to do that. Okay? So that's how we get what the gas is. And that's the only reason I've taught you about Dalton's law of partial pressure and vapor pressure, so that we can figure out what the pressure of the gas by itself is. Let's do an example problem here. So we've collected some gas, 273 milliliters. We collected it over water, which means we've pushed the water down. The temperature, 22 degrees Celsius, and the atmospheric pressure, 100.7 kilopascals. That's the outside, which means that's the total. What's the partial pressure of just the oxygen gas? Well, we need a pressure at 22 degrees Celsius. There's 22 right there. There's our number right there. 2.64 kilopascals of gas gets into the tube at 22 degrees Celsius. So the partial pressure part of the question is really easy. The total minus the partial pressure, 2.64. This is a subtraction, so we don't keep significant digits, but we keep decimals. So I'm only going to keep one decimal because my least accurate one only has one decimal. When you add, remember, it's decimals, not significant digits. So what's my number here? Need a subtraction. Yep. 98 point, and I missed that last bit. 98.1 kilopascals. So that's only the oxygen, and that's good because if we want to know how much there is, that's all we care about. How many moles of oxygen were collected? Well, if we want moles, what equation do we have to use? Very good, PV equals nRT. Do I have the pressure of the oxygen? What number is going in for the pressure of the oxygen? Yep, 98.1. Volume of the oxygen. What volume was that oxygen found in? Yep. Yeah, good conversion, 0.273 liters, must be in liters. And we're looking for R 8.314 on the back of your table if you can't remember it, but we'll use it quite a bit. And what do I need to put in here for T? Yep. 295, that's the 22 plus 273, right? 295. Now, I want to do C on this slide as well because I don't have enough room. So I'm not going to do the dividing stuff that I normally do. You go ahead and divide off. Tell me how many moles. I don't know if you guys are getting good enough, but if you've done enough of the practice problems, you're probably realizing you almost don't even need to rewrite. It's 98.1 times 0.273, and then anything else that's on this side is going to get divided off. Divided by 8.314, divided by 295. Again, if that's a multiple choice question and I don't need to see the steps, you write that out. You don't have to rewrite. Just figure out how to manipulate your calculator quickly to get that answer. What do we have for number of moles? Do we have a number yet? 109. We like that one? Okay. Now, very often, if we're comparing an experiment that one scientist did in one area compared to another area, we need to convert that gas to a certain standard value. So what if this experiment was done at SATP? What would its volume be at SATP? So when we say dry oxygen, it means we've subtracted off the water, and we want it at the second property of SATP. And so this can be done in a couple of ways. Now that we know the moles, we could stick it back into a PV equals nRT equation and solve for a new volume, or we could use the combined gas law, because I have a volume, a temperature, and a pressure, and I'm now going to have another temperature and pressure, and I could solve for volume. So because I have two conditions, one where the experiment we did in the laboratory, and the other one is the standard conditions, we can use the combined gas law for that. So let's go ahead and do that one. P1V1 over T1 is equal to P2V2 over T2. My first conditions can be all of the conditions that I started with. Pressure. Now, the pressure of the dry oxygen gas, 98.1. That's why we did this whole thing. 98.1. Volume of my starting gas, 273 milliliters. Because we're using the combined gas law, we could leave it as milliliters. We're just going to get milliliters at the end. 273 milliliters. T1. What's the temperature we did our experiment at? 22. It's got to be in Kelvin. 295. P2. What's standard ambient pressure? Yep. That's standard pressure. So it's the other one. Standard ambient pressure. Yep. 100. 100 kilopascals. We're looking for the dry volume, V2. That's what we're solving for. What's standard ambient temperature? That's the laboratory conditions. 25, right? Because very rarely do we keep the laboratory at 0 degrees Celsius. And I need it in Kelvin. Yep, 298. And I also do not have enough room on my slide to manipulate this. 298 has to come up top. 100 has to go down below. I'm just going to put a V2 equals, and I need you guys to finish that off for me. And because I left my volume in milliliters, I will have a unit of milliliters. Yep. So we're dealing with 3 significant digits across the way, so 271, right, for 3 significant digits? 271 milliliters. Okay. So there are some practice problems